Hello, everyone. This is Tyler English. I'm here to talk about a quicksort algorithm and how you would use it. So, what is a quicksort algorithm? Well, a quicksort algorithm is an efficient sorting algorithm using a divide and conquer either for uh, can be large data sets or so. Um, here are some examples that we could use. Just basic sorting. So like let's say we want to sort books by author names or just book by title names. We can do that from there. Um, with its divide and conquering style. We can sort large data sets relative to what we want to sort it by. Because it uses a low memory um, sequence. Usually it's a n place sorting algorithm. So anything n place we can just use. And it's really fast. So usually we can do it online if it's low memory capacity. Um, there are two important steps within quicksort. We have this pivot and we have this thing called partitions. So pivot is a key element, well, around which the array is partitioned. Um, meaning, well, usually we have the pivot be the last element in the array. Um, so, or just any element in the array. So, and then partitioning or would be it divides the array into two parts, elements less than the pivot and elements greater than the pivot. So let's say we have um, a random array of like 1 to 10, and our last element's 8, 3. Then our array would be divided into two subarrays, one being less than 3, and one being greater than 3. That's how it works. So basically, just an overview, it selects a pivot to partition the array, then recursively sorts the subarray. So here's an example of how it look like. So let's say we get an array, we don't specify a pivot, or we don't give it a pivot. So usually we would grab the last element in the pivot, or in this array, I mean, and based off of this 8, we would select elements that are less than the pivot, which would be the A, or elements rated to or equal to the pivot, which would be um, the rate that's higher. So how this would work is, so we have 20, it would go into the larger one since it's greater. 2, we go into the lesser one. 9, go into the greater one. 7, lesser one. 12, greater one. 15, greater one. 1, lesser one. 6, lesser one. So then we would select a another pivot based off of these two subarrays since it's recursive and split it based off of it. So with the 6, we grab the lesser one and the greater one. 2 being going to this one, 7 going by itself right there, and then 1 going to this lesser one. Then let's go over here to the higher one. So we select the last element, which would be 12. That's our pivot element. So it goes right there. 15 is higher, so it goes to its higher one. 9 is less, so it goes to the lesser array, subarray. And 20 is higher, so we put it there. Now we would select another pivot, which is this is the recursion, and then 1 there and 2 is greater, so put it there. Same with here, 15 lesser, then pivot. We don't have something higher than it. But the cool thing about this is Once we get to this point, we do not have to go all the way back up to the top, meaning the divide and conquer part. So once this is done, we have the let's sort it already. It's already done, and we can just return these values right here, which is really cool, actually. So how would you rate this? Well, here's a pseudocode for it. So we have our function quick sort, A being our data set, array, or something we want to sort, a low being the low index, high being the last index, or I guess low being the lowest one, high being the highest one, which would be the last element or the lowest element. So if low is less than high, meaning there's no other element, then we would wait, never mind. So in this Hoopsville thing with A, low and high values, if low is less than high, then we would partition it first, which would be A, low and high, meaning we would, if we go back, meaning we would divide the array into two parts, then we could shoot quick sort A, low, and then P minus 1, and then quick sort A, P plus 1, and high. Then in our partitions, we would look at A, low, and high. Meaning, so pivot A is equal to A of high, I is equal to low, for J is equal to low to high. So we would go do the elements. If A is less than A of J is less than pivot, then we would swap high with A of J, meaning we would take the lowest one and swap it with J. Then I would equal I plus 1. So we would put the lowest values on the first, or I guess we would reverse and the highest values first. Then the last thing is swap I with A of high, and then return I. So what makes this thing so good? Well, it's on its time complexity. So we have these things. So our worst would be n squared, meaning we would hit this every single time, then we would go through this whole thing every single time, doing all these actions every single time, meaning it would be O of n squared, meaning we would constantly be having to go over it over and over again. Best and average should be n log of n. So of course we have to look through all the values, hence the n, but then we really don't have to hit this. We just, so let's say this whole data set's sorted already. We just look at for J is equal to low to high, then we just go through this without hitting this if statement. And space complexity is O log of n, meaning this right here. If A of index J is less than pivot, swap A index I with A of J. And I equals I plus 1. And then, yeah. All right, so here's my code demonstration. I'll be doing this in C#, if you want to follow along. So the first step is to actually call the sort, which would be right here. Since we would be putting in is just the data if we are using this. So the first step is to sort data by low and then by high, which would be count minus one. Now, so what this is going to do is going to send us to this function. So if on our previous code, we looked at first, if first is less than last. So if first is less than last, what do? We would partition this. So partition would be consistent of and finding the pivot. So pivot index would equal partition of data first and last. So we have, well, it's gonna split the array and get the index of the. So what do we do now? We need to sort data below the pivot. So first we'll pivot index minus one as in our pseudocode, and then sort by data pivot index plus one, since this one would be the higher and this one would be the lower, and then so in this case, this would be our recursion step, which would sort it's before and after the partition or partition. Now, these two are the easy stuff, sorting and pivot. Now let's go up here to the other step, which is partition. So the first thing to do is choose the last element of the data. In this case, I'm using a list of iComparables. So what I want to look at is iComparable of pivot, which would equal to data last. Saying, so this has to be consistent with what these values are. Now I want my index, my low, so to be first minus one. Now this next step is we need to rearrange the elements around the pivot. So my first step is to make that loop. As you saw in my pseudocode, we need to make j. And j is equal to first. J goes until the last element or last index minus one, and then J++. So then our next step is to do the comparison. So we saw if um, J is less than pivot, then we swap. So in this case, we're using a comparable. So we do something called compare to um, compare J to a pivot to see if the value is less than. So 0 means it's true. 0 means it's false. Yeah, 0 means it's true. So we will have to swap these elements. So I plus beta I with beta A. So we do comparable to make a temp value, which would be data I. Then we would do data I is equal to data J. Then we would do data J is equal to temp. And then we're almost done. So the last couple things is we need to place the pivot. So you do R variable pivot swap equal to data of I plus 1, and then data of I plus 1 equal to data last, and then data last is equal to pivot swap. And then what we return is what I'm going to return is the index position of the pivot in I plus 1. And this should be the code of how we would do this. Now, I have a test here that will test this code. So I have 3 test cases. This is what a sorted array should look like for the first test, and this is what we're putting in. So raw data equals new list variable unsorted array. Then we're going to sort the data, and insert that data that's equal this, and then insert the class. Second one is sorted array. I'm gonna take this data, put it in here, do the same thing, and then make sure it's equal to this again. And the last one is if I have an empty array, I'm making a new thing, data. Am I going to be receiving the array as well? So it's on the test. Give it a second. The theme is still building. Test three, been okay. Test two, did it. Oh, test one. Test one, finished. As you can see down here, this one, two, three, they all finished. Thanks.